So your first question is the easiest one. Just tell us your name.
Hi, I'm Claire Sampson.
I'm Tara Yang.
I'm Chai Kim.
I'm Madeline Schemmel.
Claudia Landau.
Okay. Should we begin? Okay. Hello, we are Team 5057, and today we will be presenting our solution on the value of higher education. Our primary goal was to help high school students make informed decisions about their options for higher education. In doing so, we first created a model that would analyze the cost of college, and then provided a way for students to visualize the benefits that they might receive from different college paths. In the end, our model is customizable and accessible, and can be used to investigate the value of higher education. Considering the rising cost of college in the US, we wanted to create a model that would accurately predict the total cost of college for a specific student. We noticed during our own college search that many of the existing models are only limited to scholarships, tuition, and financial aid, and do not take into account the many other factors that contribute to total cost. Thus, we chose to incorporate more nuanced factors, allowing us to create a comprehensive model that would provide students with an accurate estimate. Here you can see our primary equation, which is a function of the number of years a student spends in college. We chose to focus on 4 overarching categories because we felt they would encompass the most significant factors contributing to the cost of college experience. Our largest component is institutional expenditures, which includes tuition, school fees, and room and board. Our second component is cost of living. This function accounts for the many factors that we felt were missing from existing models. We wanted students to be aware of these extra expenditures, especially since many high school students will be economically independent for the first time as they leave home. Our third component accounts for the money that students will receive to help pay for their institutional expenditures. One of the possible weaknesses of this section is that we relied heavily on student inputted values from an online FAFSA calculator. However, because FAFSA is a national standard for financial aid, we felt this allowed our model to be realistic and accurate. Income is the most significant and fluctuating independent variable, so we knew that it was important to ensure that any component dependent on income, such as financial aid, was correct. Finally, some students may take out a student loan, so our finance charges component accounts for the total amount of interest that one would accrue while paying off their debt. Here you can see a part of our total cost schedule, which is to be filled out by the student. Ideally, we would create a program that would use our equations to calculate the total cost from the student's inputted values. This program would also output the breakdown of the cost, so that the student can see the weight of each component. This would allow the student to analyze the impact of each factor. For example, if a student is tight on money and sees that travel is contributing greatly to their overall estimate, they may want to consider a school closer to home.
In order to better visualize our model, we plotted total cost against different incomes for a sample family with 2 parents and 3 children. The graphs reflect the increase in total cost as income increases and show how cost levels out as income surpasses the threshold after which a student no longer qualifies for financial aid. Both graphs are asymptotic and display a similar shape. However, the graph for the private university is significantly elongated both horizontally and vertically, with a 10-fold difference in scale of income on the x-axis, since financial aid is given to a wider range of incomes at a school with a larger endowment, such as Yale. Overall, these graphs display the flexibility of our model and how it can be tailored to a student's specific economic situation and college of choice. We feel our model is comprehensive and realistic as it encompasses the many factors that affect total cost. In fact, we tested our model on one of our friends. This student who lives in Connecticut is going to a private university in San Diego where she received an institutional scholarship. Using our model, her total cost came out to about $42,300 with a cost of living and travel at around $7,000 per school year. We found each component to be realistic. For example, our model estimates her round-trip plane ticket cost at about $720 each, which falls exactly within the range of current ticket prices. This scenario further shows how student-specific our model can be. However, we do want to address some possible weaknesses. Firstly, we decided not to create a model that would take into account economic fluctuations such as inflation. Instead, we based our model in 2015 dollars because we felt it would be more accurate to focus on the current cost of a college education. However, our model can be easily adapted for the future simply by modifying the constants in our equations. Secondly, in our total cost schedule, we rely on the student to input many of the values, so some of their projected costs may not be completely accurate. We justified this because we wanted the model to be as specific to the student as possible. Finally, we also analyzed how Obama's proposal for a free community college would affect our model. We found that it would have a minimal effect because the institutional cost for community college for low-income students is already, for the most part, covered by various forms of financial aid. So the only students that this proposal would apply to are those who do not qualify for the maximum amount of financial aid but still want to attend a community college. These scenarios can be accounted for in our scholarships and financial aid variable.
When looking at expected opportunity from various levels of education, we try to quantify financial stability, earning potential, and student debt. The first part of financial stability takes into account workplace injury, which is the probability that an individual is healthy enough to work at their job. We chose workplace injury as one of our criteria because in some jobs, such as construction working, individuals are more likely to suffer a workplace injury as opposed to a job that involves working in an office. Furthermore, we only take into account injuries sustained in the workplace because injuries sustained elsewhere are not a consequence of the education level obtained. The next part of financial stability is the future outlook of a job. In some cases, jobs that are growing have increasing salaries. On the other hand, jobs that are decreasing have lower salaries. This makes some career options and degrees more attractive than others. While the variation is most likely not linear in reality, we believe the equations provide a good approximation of future salary changes in a specific career. We modeled earning potential as a logistic growth function because realistically, wages are likely to start off at an entry-level salary, and assuming the individual advances in career, salaries ultimately level off at a peak wage. By assuming most individuals enter the workforce upon leaving college and work until the age of retirement, 65, we scaled our logistic growth model using the experimentally determined scaling factor K. We believe this model gives a realistic estimate of the change in wages over time, allowing us to calculate earning potential as a function of time. The third part of our model is student debt. Many federal loans are designed to pay off after 10 years, so we use this assumption in calculating the amount of student loans paid off per year. Improvements to the model would include making it more flexible to the various types of student loans. In addition, our model does not take into account the reality that student individuals can pay out varying amounts of debt per year.
Okay. These factors are combined into a calculation of the monetary benefit of each level of education. The value F is a function of time that can be calculated at various years after the individual's entrance into the workplace. Next, in order to give our final calculations more meaning, we converted them into a coherent and easy-to-understand ranking system. To do this, we compared the F value to a calculated baseline to get scales for both the long-term and short-term benefits of higher education. Both the long-term and short-term scales are incorporated into our final ranking. In order to compare the different F values, we calculated a baseline value using this function. The baseline value, B, is just the monetary gain function calculated for the average American. When developing our ranking system, we took both short-term and long-term considerations into account. This is especially important in representing situations where the long-term and short-term values are drastically different. For example, if the individual initially has to pay off large amounts in student loans but later earns higher wages. While our model does consider both short-term and long-term effects, it only accounts for two extremes on the monetary gain function. In order to improve the accuracy of our model, we could have integrated the monetary gain function and then compared this to a different baseline value. This would have taken the monetary gain of each year into account rather than just the monetary gain from 2 points in time. Finally, we tested our model by calculating rankings for each of these scenarios. However, it is important to emphasize that these rankings can be calculated for a variety of other scenarios, including specific colleges and major choice. These rankings, which are based solely on monetary gain, act as a base value, which we have graphed. In Part 3 of our model, we will take into account the other factors that affect college choice and add these to our base values in order to create a final graph that analyzes the individual's college options.
In Part 3, we designed a survey which high school students could use to help decide which educational opportunity would give them the greatest quality of life or make them the happiest. We studied existing factors of happiness and theories of psychology, then created an adaptable, transparent set of criteria that doesn't order students to a specific path, but rather allows them to make the best use of available data. I will now walk you through a hypothetical in which a student, Moody, takes our survey. As we progress through the slides, the different educational opportunities will accrue value in accordance with Mandy's responses. Our first criteria doesn't vary among students. It encompasses quantifiable factors of happiness, those that are positively correlated with wealth. For example, those who have more money are better able to purchase healthcare, education, and cultural experiences. We use the values calculated in Part 2 of the problem to represent a cost-benefit analysis of the different educational opportunities. This section's weight of 4 was set arbitrarily. The other weights have been set in relation to this one. This is a graph of the Part 2 values. It's simply a representation of our determination that financially, a student's best option is to obtain a STEM degree from a public school. Our second criteria refers to the unique predisposition to happiness that all individuals have. According to psychological theory, while a person's level of happiness can briefly fluctuate due to life events, eventually it will always return to a constant level. This means that some people are inherently more predisposed to be happy than others. These people are more able to enjoy life and thus have more flexibility when it comes to choosing their paths because they don't need to compensate for a low baseline happiness. This section weight of 2 reflects the fact that research has shown significantly more factors of happiness that can be bought than hinge on baseline happiness. Here's a graph of Mandy's baseline happiness. We calculated the value by asking Mandy to rate the amount of happiness she derives from her various activities and relationships on a scale of 1 to 3. We kept the scale small in order to mitigate the poor accuracy that is known to result when subjects are asked to describe their feelings. You will notice that the value is uniform across all opportunities. This may make the value seem insignificant, but because our model exists not only to compare opportunities, but also to see how high an option scores out of a possible 12 points, we believe it is important. Our final criteria calculates Mandy's likelihood of success based off her past school and workplace experiences and her future goals. Its 3 subsections are each given a weight of 2 for a total weight of 6, which reflects their high degree of importance, derived from being comprised of entirely personal and mostly objective inputs. First, we input Mandy's grades. As you can see, her values in this section are highest in non-STEM and non-traditional options. This reflects her high grades in non-STEM and non-academic classes. Lower values in STEM columns correlate with lower grades in STEM classes. The small bar in the high school column is representative of Mandy's overall good grades. Error in this section could result from variability in class difficulty, but the students can adjust for this at the end of the survey, as we will demonstrate. Next, we look at Mandy's employment history in order to determine her current workplace readiness. This value is the same across all options because they all lead to employment. However, it mostly exists to help Mandy evaluate ending her education after high school, as it is not immediately relevant to the other options. Note, we are making the assumption that Mandy will work post-high school if she does not continue her education. Finally, in the only opinion-based subsection, we look at Mandy's life goals. They're fairly modest, as this value is on the larger side, indicative of the fact that Mandy's choices in life can be driven more by what makes her happy and less by monetary constraints. At this point, the graph is complete, and we can see that Mandy's best ranked choice is to obtain a non-STEM degree at a private college. However, due to the graph's transparent nature, Mandy can also use her own judgment. For example, Mandy also showed a high propensity for non-academic classes. Maybe she feels that, although she excelled in woodshop and English, she enjoyed woodshop more, and thus would prefer to pursue a 2-year degree at a technical school. It is likely that Mandy would be happy at any of the 5 higher-ranked options. Additionally, one of our own group used our model to rank the various colleges she was considering. As mentioned earlier, with the right data, Part A values can easily be calculated for more specific options. Note that each of these options was considered STEM because that is the type of degree our group member will be pursuing. Interestingly enough, she will actually be attending the second-ranked college on this list due to her finding it to be a better fit. Again, this shows how our model's transparency allows for students to consider externalities. Finally, we had the same friend we used to test the total cost model to use this model to help choose between a STEM degree and a humanities degree within the college she will be attending. The graph indicates that she would be happier studying the humanities, but she feels she challenged herself more in high school STEM classes, thus explaining her lower grades there. Our model reaffirmed that both majors would be good choices, and that if she feels the data were swayed by disparate class difficulty, she should indeed choose the major she feels most passionate about. In our effort to calculate the true cost of college, we successfully worked together to determine the monetary costs and benefits of various educational paths, as well as their less tangible values. We combined the disciplines of math, social science, and psychology to create a complex solution that is both specific and adaptable. Our model draws strength from the fact that it is designed to be transparent and flexible, not infallible. It can bend to suit as many circumstances as there are graduating high school seniors, but it will never break. Thank you.
Dr. Bliss?
So I have a pretty technical question, and I want to go back all the way to part 1. So if you guys can go back. I'm looking in particular for the equation for total cost.
Yes.
There you go. Okay, so when you In this equation, you're summing up the alpha of n and beta of n, those institutional expenditures and cost of living. You're summing those up from I equals 1 to n. In the table where you explained what alpha of n and beta of n are, they both have a factor of n in those equations. Can you explain?
Yeah, we realized more so after the fact when we were kind of proofreading it that we actually we put it in both places accidentally. The way to fix that would be to remove the n that's multiplied by each of the terms and just leave the summation. So that was just a fault on our part. Yeah.
On the same chart in the paper, we noticed that the gamma results were 85.18 for all cases. And that was the interest that the student would have to pay. And so can you explain why it was the same across all 6 cases?
Yeah, so we just assumed that the student would take out the loan. When you enter in their information in FAFSA, you can take out a federal loan that's subsidized by the government, I believe. And we just assumed that the student would take out that loan and pay it off in the same amount of years and with the same interest rate in order to simplify our model. But for the unique student, when the student's actually taking our model, they would enter in their own information. So this was just for the 6 scenarios that we played out.
So at the end of part 2, you had a histogram that was sort of comparing STEM versus non-STEM and public versus private. And it seemed as though STEM was beating non-STEM, but public and private seem really similar for both STEM and non-STEM. So can you tie that result back to your model and kind of explain why your model wasn't distinguishing between that choice of public versus private, and then what might help a student, how you might adapt your model, or what different inputs they might need to put in if they needed to make that choice?
Yeah, that's basically because when we calculated out the earnings someone would earn has a much larger effect in our model than the student debt one would pay. So the main difference between a public and a private school is the amount of student debt one has, because public schools are generally cheaper. But the main difference between a STEM and a non-STEM was usually the amount of money one earned in their career. So the differentiating factor was that in the differentiating between STEM and non-STEM is the earnings have such a much larger weight than the amount of student loans.
Yeah, and then in terms of how we might account for that, I think the student experience at a public versus a private school doesn't really hinge so much on whether that school is a private or public institution. It would probably hinge more on geographical factors, or whether it's an urban or a suburban or rural area. And that was something we considered incorporating into part 3 of our model, but ultimately we felt that those little variables would just make the survey too long and complicated, and that those are kind of things that students are already considering. I think most students already have in mind, I want to go to an urban college in the South. And that's something that they'll know when they're looking at their different college options.
Yeah, actually, just to add to that, I think one of the things our model focused on doing was taking really subjective things to give the student an objective response to what college they should go to. We focused on non-opinion based questions, and then after we show where everything's come from, so the student can look back on that and see use it to make their own opinions on it, so they can look at it and see what they want, and then look at where our values from our model are coming from, and then go back and it's a flexible model, so they can decide where they want to go based on the information we gave them.
I have one question. I think towards the end of your talk, certainly spent a lot of time, and I appreciate it, on the individualization of your model. I was wondering, did you take any time to investigate how changing the weights of some of your categories would affect outcome, or allowing your individuals to affect change to those weights based on their interests?
Well, yeah, we personally did not run through and look at the graph with different weights, but that was something that we were aware of students being able to do. We talked about, one of the students, the student that our friend, how she, perhaps thought that she challenged herself a lot in STEM classes in high school, and that's why the value that would be pushing her to go and take that STEM degree was lower than the one that was pushing her towards a humanities degree. So for her case, the way we worded it was like she should, consider that value less. But if you were to, the mathematical translation of that is she should weight that option less. So it is definitely something we were considering.
Yeah, I think for most of this, we really wanted students to be able to read our graphs and read what our model is producing and then sort of take it into their own. For example, if the school that we say they should be going at or should be considering is not a school that they find that they fit well into, then they shouldn't pick that option, and they should weight different parts of our graph differently based on their own personal views.
Can you go back to explain on the short-term and long-term equations? Can you explain the denominator?
Yes. So it's anyway. So basically, for the short-term and long-term equations, we wanted to create an asymptotic function that approaches 2 as you get bigger, so it doesn't go above that. And so what we did is we created the asymptotic function, and then we added the 10,000 into the denominator sort of as another scaling factor, so it doesn't reach 2 too quickly, or like it takes just the right amount of time to get there, based on like how we wanted our models to be like aligned. Because if everything is just given the value of 2, then that's not really an accurate representation. But if our model is too strict, then it doesn't really give everything comes out as like not a good option. So that was sort of to make sure we get to our model is exactly how we want it and the values are within the right range.